In episode 14 of the CySec101 training series, we are going to be talking about networking essentials, and this is the continuation of the networking module that we started in episode 13, and it's part of the Cybersecurity 101 pathway of TryHackMe. And it's a really big module, the networking module. We have, I think, maybe 7 or 8 rooms that we're going to be covering. So this is just basic continuation of what we're going to be talking about with networking essentials. We did like the networking introduction in the last one, networking components, I believe. And then we're just going to be going through essentials, and then we'll start going through networking security and protocols and so on and so forth. So that is it. And real quick word from our sponsor, and then from there we'll jump into the introduction. This video is sponsored by Hackaholics Anonymous, the premier membership community for security professionals and hackers, and you can get access to 4 levels of perks and benefits, starting with the cyber supporter that gets their own Discord server and access to me directly, as well as all of our advanced members, and then the advanced level members like the cyber agent and the cyber guardians that get Python automations and exclusive content, exclusive downloads, live streams, their own Discord servers, and a variety of other benefits that are honestly really amazing, and I think they're an excellent bang for the buck, so to speak. To join Hackaholics Anonymous, you can click the link in the description below. You can go to our YouTube channel and click join, or you can essentially go to youtube.com/@hankhackshackers/join, and you'll be taken directly to the join page. Hopefully I will see you in the Hackaholics Anonymous community and in the Discord chats. Now that's out of the way, let's actually get into the introduction of the networking essentials. Alright, so have you ever wondered how your computer can dynamically configure its network settings when you turn it on or connect it to a new network? Have you ever wanted to know how many devices and countries your packets pass through before reaching their destination? Are you curious how all your home devices can access the internet even though your internet service provider gives you a single IP address? These are all nerd questions, right? So if you want to know the answers to these, this is what we're going through today. Last video we talked about networking concepts. Today we're talking about networking essentials, and then we're going to go through networking core protocols and secure protocols in the next couple of videos. And today we're going to go over the ISO OSI model and the layers of it, the TCP IP model and the layers of it, as well as the Ethernet IP and TCP protocols. So we touched on them in the last video, but today we're going to take a deeper dive into those concepts. We are going to learn about the dynamic host configuration protocol. We're going to learn about address resolution protocol, the network address translation, and of course internet control message protocol, so the ping and traceroute tools, as well as just what they do. So that is essentially the gist of today's video, and without further ado, let's actually talk about the dynamic host configuration protocol, DHCP. All right, if you can imagine connecting to a new Wi-Fi, so your laptop connected to the Wi-Fi of your favorite coffee shop, and automatically configured the network so you could now work on a new TryHackMe room while you're in the coffee shop. You didn't type an IP address, but your device is still all set up. So how does that actually happen? Whenever you want to access a network, at the very least, there are a few things that need to be configured. Number one, the IP address along with the subnet mask, and this is the IP address of your computer, right? Your router or the gateway, as well as the DNS server. All of these things need to be configured in order for you to be able to access a network, a Wi-Fi network, for example. Whenever you connect the device to a network, those things must be set according to the new network, right? So, for example, in this case, the coffee shop Wi-Fi, right? Configuring these settings is a good option, especially for servers. Servers aren't expected to switch networks, so you can essentially set them up and you don't carry the domain controller and connect it to the coffee shop Wi-Fi, right? You don't carry this big box with you that is the size of a room, basically. So other devices, however, need to connect to the servers and expect to find it at a specific IP address, meaning that IP address should not be dynamic. It should not be changing. It should be static for the most part. So when you have an automatic way to configure the connected devices, you have a lot of different advantages that come to play. Number one, it would save you from the time and energy to manually configure the network. And it's very important, especially for mobile devices like a laptop. Number two, it saves the address conflicts. So you getting somebody else's IP address, for example. So if two devices are configured with the same IP address, there's a problem that takes place. So you don't want to do that. The IP address conflict would prevent the involved hosts, the involved computers basically, from using the network resources. And this applies to local resources as well as the internet. So the solution is inside of our dynamic host configuration protocol. The DHCP is an application level protocol that relies on the UDP, the user datagram protocol, and the server listens on UDP port 67 and the client sends from UDP port 68. The smartphone and laptop are configured to use DHCP by default because it's dynamic. They move around, so they need to be dynamic, right? So the process is, you discover whatever the network is, you make an offering, and then the request, and then the acknowledgement, right? So that's kind of the whole idea here. So DHCP discover is by the client. The client broadcasts a DHCP discover message seeking the local DHCP server if there is one. Then the server responds with the DHCP offer message with an IP address that would be available for the client to use. So the DHCP server says, these are the IP addresses that I have available. And then the client responds with, okay, well, can I have whatever one that is available? Just give it to me. I'll take that request. They make the request, the client, meaning your laptop, basically. Your laptop makes the request, and then the server responds with a DHCP pack message to confirm that the offered IP address has now actually been assigned to that client. So, you send the discover, the server responds with an offer, you accept the offer with your request, and then there's a DHCP acknowledgement saying, okay, so here's your IP address. Now, what happens is that this is a leased IP address. I don't know if we're going to talk about it, but it's called a lease, meaning it's not a permanent assignment. It will change the next time that you connect to that Wi-Fi router, for example, right? So the following packet capture shows the 4 steps explained above. In this example, we actually end up with this particular private IP address. If you remember from the last video that we did, if it starts with a 10, a 17, or a 192, or 10, 172, and 192, that means that they are private. So if we run tshark, it'll search for searching through the pcap file from the DHCP. We can see that these are the transactions that took place, right? This was the conversation. So there was a DHCP discover that was sent from our machine. Then there was a DHCP offer that came from the actual server, and then we made the request, and then finally we ended up with the acknowledgement, and this is what we actually got as our IP address that was assigned to us, right? In that exchange, we can notice the following. So the client starts without any IP network configuration. It only has a MAC address, and the first and third packets, the DHCP discover and request, the client searching for the server still has no IP network configuration and has not yet used the server's offered IP address. Therefore, it sends the packets from the 000 to the broadcast IP of 255 times 4, basically. As for the link layer, in the first and third packets, the client sends to the broadcast MAC address, which is just a series of Fs because they are not shown in the actual image above, in the output above. The DHCP server offers an available IP address along with the network configuration in the DHCP offer. It uses the client's destination MAC address and then the proposed IP address in this example system. So the link layer, meaning the MAC address layer, the first and third packets, we send it to the MAC address, which is not available in the display that we have over here, but it basically sends it to the MAC address because there is no actual IP address, right? And then once it is sent to the MAC address, the server offers an available IP address along with the configuration that is available in its offer, and then it uses the client's destination MAC address so that it will essentially assign that instead of this blank one right here, or this like generic one. At the end of it, the device would have received all the configurations that it needs to access the network or even the internet. In particular, we expect the DHCP server has provided us with these things: the leased IP address to access network resources, gateway to route your packets outside the local network, and a DNS server to resolve domain names, and we'll talk about that in a little bit. So when we say leased IP address, just keep that in mind. That's part of the dynamic portion of this, meaning that it's not permanent. You don't get this permanent assignment of this IP address to you forever, right? Because you're on a coffee shop, you're on a public Wi-Fi. So, you know, most likely you may not visit that coffee. Maybe you do, right? But most people don't revisit that Wi-Fi coffee shop or coffee shop Wi-Fi. And so the whole idea is that, you know, you use it for the length of time that you're there, and then when you leave, somebody else gets assigned that thing. So it's a lease, it's not a permanent assignment. So how many steps does DHCP use to provide network configuration? And the answer to that is 4. What is the destination IP address that a client uses when it sends a DHCP discover packet? And the destination IP address is the 255.255.255.255. And there we go. What is the source IP address a client uses when trying to get the IP network configuration? I think that was the 0001, right? So it would, yeah, 000. Okay, so that is our IP address. So we're just going to do what is it? 000 and one more 0. There we go. All right, cool. Let's talk about the address resolution protocol, the ARP. In the last room, the networking concepts room, we talked about two hosts communicating over a network. And when they do that, an IP packet is encapsulated with a data link frame, and it travels over layer 2, the data link layer. The two common data link layers that we use are the Ethernet, which is on IEEE 802.3, and Wi-Fi, which is on 802.11. Whenever one host needs to communicate with another one on the same Ethernet or Wi-Fi, it has to send the IP packet with a data link layer frame. And then although it knows the IP address of the target, it needs to look up the target's MAC address so the proper data link layer can be created. So it needs both of those things, even if it's traveling over a network. It needs both the MAC layer as well as the IP address. So a MAC address is the 48-bit number typically represented in this kind of a format. It's hexadecimal, and this is another one. They're on the author's network, for example. So the devices on the same Ethernet network do not need to know each other's MAC address all the time. They only need to know each other's MAC address while communicating. Everything resolves around IP addresses. Considering this scenario, you connect via your device to a network, and if the network has a DHCP server, your device is automatically configured to use a specific router or a gateway, and then the DNS servers. Consequently, your device knows the IP address of the DNS server to resolve any domain name. Moreover, it knows the IP address of the router when it needs to send packets over the internet. In all of this scenario, no MAC addresses are revealed because you are no longer worried about communicating with somebody in your same network in your room or in your office or something like that. Now you're talking about the internet, right? So the World Wide Web. So two devices on the same Ethernet cannot communicate knowing each other's they cannot communicate without knowing each other's MAC address because, again, they are on the same Ethernet. They're in the same network. So as a reminder, in the screenshot, we see an IP packet with an Ethernet frame. The Ethernet frame contains the destination MAC address, the source MAC address, and then the type. In this particular case, it's an IPv4. Now, all of this is done in hexadecimal, so you can't really see it in this particular at this bottom portion, but it does show it to us on our Ethernet portion when we're looking at the Wireshark packet. So it has essentially for every level of the TCP IP, it actually has a section dedicated to it. And in the Ethernet portion, the link portion, we see the destination MAC address, the source MAC address, and then the fact that we're sending an IPv4 packet. So, Address Resolution Protocol, ARP, makes it possible to find the MAC address of another device on the Ethernet. In this example, a host with the IP address ending in 89 wants to communicate with another one ending in 1. It sends an ARP request asking the host with the IP address of 1 to respond. So 89 is asking 1 to respond. And the ARP request is sent from the MAC address of the requester, meaning this guy's MAC address. And it's listed as such, right? So it's not the actual MAC address. And then the ARP reply arrived shortly afterwards with the actual IP address responded with its MAC address. From this point, the two hosts can actually communicate. So the first time when it sends its request, it's sending it not knowing what the MAC address is. And then the the person that you're sending it to, or the device that you're sending it to, will actually respond with its MAC address, and now you know what its MAC address is, and then you store it inside of your database, so next time you know exactly how to communicate, or for the rest of this transaction you know how to communicate. But the first time that you send it out, you don't know what the actual MAC address is. You're kind of making a request to try to connect to them, but you do know what their IP address is. So it's like, hey, who has this specific IP address? That's the request that we're sending out. And then the computer that actually has that IP address is going to respond, and then its MAC address is included in the response. And it's like, oh, that's where we're sitting. Cool. Okay, good to know, right? So if we use TCP dump, the package will be displayed differently. It uses the term ARP request and ARP reply. And so this is what that looks like. So we have the same, it's kind of similar, but it's saying this is a request. So who has this? And then this is the reply. This is at this MAC address. And that's basically the communication on TCP dump. This communication is reading the ARP PCAP file using TShark. This one is actually looking at the traffic via TCP dump. So the request or reply is not encapsulated with a UDP or even IP packet. It is encapsulated directly within an Ethernet frame, and this is what it looks like on Wireshark. So this is, we saw that previously in the last screenshot that we had, we were looking at the actual Ethernet portion. Now we're looking at the actual ARP portion, where it's showing us the sender MAC and then IP address, as well as the target MAC and IP address. So ARP is considered layer 2 because it deals with MAC addresses. Others would argue that it's a part of layer 3 because it supports IP addresses as well. What's essential to know is that ARP allows the translation from layer 3 to layer 2. So it allows both of those to take place. Let people argue about whether or not it's layer 2 or layer 3. For your intensive purposes, you need to know that address resolution protocol is resolving the MAC address to the IP address and vice versa, so that the machines actually know how to communicate with each other either on the same network or across the internet. So what is the destination MAC address used in an ARP request? And that's the very basic one that we have, which is this thing right here. It's like the generic one. So this is the destination MAC address that we use. And then in the example above, what is the MAC address of 66.1? So the MAC address of 66.1, if we look at it here, so it says who has 66.1, and in this case, this is the MAC address at 66.1. And then we're going to go over here and paste that over here. Very good. All right, cool. Let's move on to ICMP. Internet Control Message Protocol. The Internet Control Message Protocol is mainly used for network diagnostics and error reporting. So we use ping and traceroute as the commands to essentially accomplish that. It's very commonly used. So ping and traceroute is very commonly used. Ping uses ICMP to test connectivity to a target system and then measures the round trip time. In other words, it can actually be used to learn whether or not the target is alive, and then how quickly it actually responds. Traceroute is the command that is run on Linux and Unix, and then it's traceRT on Windows, and it uses ICMP to discover the route from your host to the target. If you remember from the last video, we talked about the number of routers that a packet will go through to get from us to the destination that we wanted to get to. And that number of hops that it takes to go from one router to another, that's essentially what traceroute traces for you, right? It tracks it back for you. So if you've never actually played ping, or I guess ping pong table tennis, you can actually kind of understand what it looks like on the computer. But I mean, when you kind of think about ping pong or table tennis, it's just a ping pong, like you're just going back and forth, right? So the ping command will send a request, the echo request, and then the screenshot will actually show it right here. So we have the ICMP, Internet Control Message Protocol. That is the section for this. And it says echo ping request, right? That's what we did. And then we actually got a response that's going to be inside of the next frame that you would look at. The computer on the receiving end responds with the reply, which is right here. So the request frame is frame number 1. We are now in frame number 2, and frame number 2 is the reply of frame number 1, or the reply to frame number 1. A lot of things can prevent you from getting a reply. In addition to the possibility of a target actually being offline or shut down, a firewall can block the necessary packets for ping to work. So if we use C4, we count the number of packets, otherwise it would just run indefinitely. So when you use C4, it just runs it 4 times, and then it'll stop after the 4th time. And then it'll say 4 packets transmitted, 4 packets received. So in this particular case, it was actually up, it was running, everything is all good. The output shows there was no packet loss. Moreover, it calculates the minimum, average, and maximum standard deviation of the round trip time, which is what we have over here. So this is it, minimum, maximum, and then we have the average, and the same thing over here. So ICMP, where do we have the minimum, maximum, average? I think it's actually, this is it right here. Yeah. So minimum, maximum, average, and then the standard deviation. So MDEV, which is this one right here. The median deviation is what that would stand for. Trace route basically routes or traces the route. So how can we make every router between our system and a target reveal itself? We do that with traceroute, and it's done with the field that's called time to live. That indicates the maximum number of routers a packet can travel through before it is dropped. The router decrements the packet's time to live before before it sends it across. So by 1, meaning it'll decrement it by 1 before it sends it across. When the TTL reaches 0, the router drops the packet and then sends the ICMP time exceeded message. In this context, time is measured in the number of routers, not seconds. So the terminal output shows the result of running traceroute to try to reach example.com. Some routers don't respond. In other words, they drop the packet without sending any ICMP messages. Routers that belong to your ISP might reveal their private IP address. Moreover, some routers that respond and show their public IP address, and this would let us look up their domain name and discover their geographic location. Finally, there's always a possibility that ICMP time exceeded gets blocked and never reaches us. So we can see that this is the very first hop. This is the first packet that was sent out, and it's going from the gateway, right? And then private IP, public IP, private IP, these things didn't actually respond. And in a private IP, this seems to be, what is it? I feel like this is like the locations that are associated with those individual routers. It seems like they're in Marseille in France. And then you get some more. These are the other ones as well that go on the way. And finally, you land at the destination that you wanted to land at. So the very last hop, if it's not dropped, and if it makes it all the way to the end, it will actually be the destination that you want to look you want to connect to, right? So you can always take something like this. So let's see if this is a free room. This is actually a subscriber only room, but you can basically go to Gemini AI or Meta AI or GPT or any of the major AIs and talk to them and basically say, you know, show me a sample traceroute output and then explain to me what it looks like. Or you can just copy and paste something like this and go and have it be explained to you. But for the most part, it's just tracing the route that a packet takes to go from your gateway, from the location that is starting, to the place where you want it to end, which is example.com. So if you see that this 215.14 at the end, that's where it actually ends up at. And if it doesn't make it there, then the packet didn't survive, or it was dropped along the way, and it's mainly because there's connectivity issues. And then you can kind of see at what point it was dropped. What was the last step that it took before it was dropped? So using the images above, how many bytes were sent in the echo ping request? So if we go and look at the images here, it says how many bytes were sent. And so let's see what we got over here. 64. What am I saying? It's literally right here. I don't need to go any further than that. So 64 bytes were sent. And that's typically what it looks like with every single one. The echo ping request. We sent in the echo ping request. Oh, so maybe we're looking at the wrong one. So over here, inside of the echo ping request, how many bytes were sent? And so if we go and look at the data here, we have 40 bytes. There you go. 40 bytes were sent. That's the number that they're looking for. I was looking at the wrong section there. So there we go, 40. And which IP header field does the traceroute command require to become 0? So which IP header field does the traceroute command require to become 0? My bad, it's TTL. TTL needs to reach 0. That's completely my bad. See, you learn things, right? You go through these things and you learn things, and I'm learning with you because I haven't gone through this room before, and I am not a master of networking, so I'll admit that straight up. Obviously, if you haven't been able to tell. Okay, cool. So now let's talk about routing. So considering this diagram below right here, it only has 3 networks. However, how can the internet figure out how to deliver a packet from network 1 to network 2 or network 3? That is an overly simplified diagram, obviously. We need some algorithm to figure out how to connect network 1 to 2 and to 3 and vice versa. So we have network 1 over here, we have network 2 and we have network 3. So considering this, how does the internet figure out what it is that you are trying to do and where you're trying to go, right? So let's consider a more detailed diagram. The internet would be millions of routers and billions of devices, and the network below is a tiny subset of the internet. The mobile user can reach the web server. However, for this to happen, each router across the path needs to send the packets via the appropriate link. Obviously, there's more than one path. Route, meaning one path being route, connecting the mobile user and the web server. We need a routing algorithm for the router to figure out which link to use. So we have the mobile user trying to get to the web server, right? So this is actually the diagram that we looked at in the last video. So which route is it going to take to end up here? At the very least, the fastest one would probably be boom, 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 and then right here. But sometimes it may be boom, 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 boom here, right? So it depends on what is available. It's one of the big pieces. But the whole point is that there needs to be an algorithm that will figure out which one to use. So this is where it kind of gets a little bit technical. So the routing algorithms are beyond the scope of this room. However, we will briefly discuss a few routing protocols so that you can become familiar with their names. So OSPF is the open shortest path first. It's a routing protocol that allows routers to share information about the network topology and calculate the most efficient paths for data transmission. It does this by having routers exchange updates about the state of their connected links and networks. This way, each router has a complete map of the network and can determine the best routes to reach any destination. So OSPF, the shortest path first, and it's done by finding the entire map of the network essentially. And once you have those updates constantly being shared, then the router has a complete map and knows exactly the best route to reach the destination. The next one is EIGRP, so Enhanced Interior Gateway Routing Protocol. EIGRP is a Cisco proprietary routing protocol that combines aspects of different routing algorithms. It allows routers to share information about the networks they can reach and the cost, like the bandwidth or delay association with those routers. Routers then use this information to choose the most efficient path for data transmission. So EIGRP is a Cisco proprietary routing protocol. It combines aspects of different routing algorithms and allows routers to share information about the networks they can reach and the cost, for example, how long it will take and how much resources it will take associated with those routes. And then the routers use this information to choose the most efficient paths for the transmission. BGP is the Border Gateway Protocol. It's the primary routing protocol used on the internet. It allows different networks like those of the ISPs to exchange routing information and establish paths for data to travel between these networks. BGP helps ensure data can be routed efficiently across the internet, even when traversing multiple networks. So this is the primary routing protocol on the internet, and ISPs, internet service like AT&T and Spectrum, for example, they exchange routing information to establish paths to travel between these networks, and they help ensure data can be routed efficiently across the internet when traversing multiple networks. RIP does not mean rest in peace. It's the Routing Information Protocol, and it's a simple routing protocol often used in small networks. Routers running RIP share information about the networks they can reach and the number of hops that it's required to get there. As a result, each router builds a routing table based on this information, choosing the routes within the fewest hops, to reach each destination. So this is for the smaller networks. BGP is for the internet as a whole, we have EIGRP, which is a Cisco proprietary routing protocol that combines aspects of different routing protocols. And then you have the open shortest path first, which is allowing routers to share information so that you can get the most efficient path to get across. So which routing protocol discussed in this task is a Cisco proprietary protocol, and it's this one, EIGRP, the Enhanced Interior Gateway Routing Protocol. So here we go. Drop that in there, and let's move on to the NAT, the Network Address Translator. So in networking concepts, the last room, we calculated that the IPv4, the version of IP addresses that you see that is the, the 10 dot, whatever dot, like the basic one that pops into your head when you think of an IP address, it can support a maximum of 4 billion devices. Because there are so many other devices, there are way more than 4 billion devices, computers, smartphones, whatever. It was clear that IPv4 would be depleted quickly. So one solution to address this was the network address translation. And the idea behind NAT is to use one public IP address to provide the internet access to many private IP addresses. And in other words, if you're connecting a company with 20 computers, you can provide internet access to all 20 computers by using a single public IP address instead of 20 public IP addresses. So technically speaking, the number of IP addresses is always expressed as a power of 2. To be technically accurate, with NAT, you reserve 2 public IP addresses instead of 32. Consequently, you would have saved 30 public IP addresses. So the whole idea here is to what? Use one public IP address to provide the internet access to many private IP addresses. Unlike routing, which is a natural way to route packets from destination to host, or from destination host to the from support. What am I saying? From the source host to the destination host. I literally lost my mind. Unlike routing, which is the natural way to route packets to the destination host from the source host, right? Routers can support NAT, must find a way to track ongoing connections. Consequently, NAT supporting routers maintain a table translating network addresses between internal and external networks. Generally, the internal network would use a private IP address range, while the external network would use a public IP address range. So what you can expect is that, number one, privacy-wise, the outside world isn't going to see your private IP address, but then functionality-wise, because there is so many more that needs to be accessed in a public network out in the public internet, you can use one private IP address to get a hold of many different public IP addresses. Multiple devices can access the internet via a router that supports NAT. The router maintains a table that maps the internal IP address and port number with its external IP address and port number. For instance, the laptop might establish a connection with some web server. From the laptop's perspective, the connection is initiated from its private IP, which is this thing, and the TCP port number, which is 15401. However, the web server will see the same connection as being established from this IP, which is a public IP, and a TCP port 19273. So the router does this translation without you even thinking about it. It's doing it in a fraction of a second, right? And so this is the whole idea here, that the laptop right here, or the cell phone, either one of these things, if it wants to access the internet, it goes through the router, and the router translates this private IP to a public IP so that the internet can see it. So in the diagram above, what is the public IP that the phone will appear to use when accessing the internet? So the one that the phone is going to use is 0137. So 0137 will end up using 212.3.4.5 is what it's going to end up using. So 212.3.4.5. And assuming that the router has infinite processing power, approximately speaking, how many thousand simultaneous TCP connections can it maintain? And we're going to say 65 because there are 65,000 ports. So assuming that it has infinite processing power, we can say it's approximately 65,000. So basically one for every port. And that was it for the network address translator. And really, that was it for the networking essentials that we were talking about. It was kind of a quick little run through here, mostly a lecture. And then we have this one little exercise that's left for us. So I'm going to zoom out real quick, and then we're going to run through the exercise, and then we're going to get our flag, and then we are going to wrap it up. So let's do it. This room introduced us to a variety of protocols. We have covered these things. Although we use the internet daily without coming to access most of the acronyms, these protocols are the foundation for a functional network. So please follow the instructions to get the flag. That's basically what we're doing here. So it says, which protocol do we need? As we have learned in this room, different protocols and techniques are used to solve various problems. In this exercise, we will go through this. Okay, so let's actually start it. So here we go. I want to find out the DNS server and the default route on a network automatically. Which protocol should I use? So we want to find out the DNS server and the default route. Which one do we use? Is it ICMP? Is it Network Address Translator, ARP, or DHCP? And the default route on a network automatically, I'm going to go with DHCP. Very good. Cool. I want to find another host's hardware address, which is the MAC address on the network. Which protocol lets me do this? And that would be the address resolution protocol. Very good. I want to confirm that I can exchange packets with another host as if I am playing ping pong. Which protocol supports this? That would be ICMP. And then we need to give 25 devices internet access. However, we only have one public address. That would be the Network Address Translator. And just like that, we have completed the exercise. Easy money. Let's go. So ready. I'm so happy that this is working. Okay, great. So, and here we go. We're going to click on that and we're going to get notified of the success, and we are officially done. Congratulations, ladies and gentlemen. Hopefully you made it through this whole thing with me as well. So if you found value from this video, or if you want to get the next series of videos that are going to come out from the CySec101 training series, I do encourage you to like, subscribe, turn on the notification bell, drop a comment, all that good stuff, because there is going to be regular videos coming out in CySec101. There's also a new training series for Security Plus that's going to be coming out in the next couple of weeks. So if you want to get, jump start on that, I would highly recommend that as well. And you can even get early access to that by becoming, again, one of our subscribers. And then you can also join Hackaholics Anonymous, which brings me to the Hackaholics Anonymous membership community, which is the premier YouTube community for security professionals and ethical hackers. And you will get access to 4 tiers of memberships. So the cyber supporter, who gets early access to content, they get their own Discord servers, as well as access to me and all of our advanced members. And then we have the cyber agents and the guardians and the masters, who get Python automations every single month. They get live streams with me. They get their own Discord servers. They get exclusive content, exclusive downloads. For example, all of the notes that will come from Security Plus upcoming, as well as the practice questions and the practice examinations, so on and so forth. All of that is reserved for all of our advanced members of Hackaholics Anonymous. So to join Hackaholics Anonymous, you can click the link in the description below, or you can go to our homepage on the channel and click join, or you can go to youtube.com/@HankHacksHackers/join, and you will be able to join Hackaholics Anonymous. I really do hope to see you inside of the Discord servers. At the very least, I hope to see you inside of the comment section of the channel. And that's pretty much it for today. This is your boy Hank Hackerson at Hank Hacks Hackers, your favorite network and system attacker/protector. If no one else loves you, Hank loves you. Love, peace, and chicken grease. I think by the time that this comes out, Christmas will have come and gone. So I think it's probably going to be the day after Christmas, or maybe the weekend of something like that. But it'll definitely happen after Christmas, I think. So hopefully you got a lot of value out of this channel. We are literally right around the corner with the new year, and we're about to hit our 1-year anniversary with this channel. So it means a lot to me that you're here. It means a lot to me that you're watching, and I really hope that you're getting a lot of value out of this channel. I do look forward to seeing you in future videos, and in the comment section, again, love, peace, and chicken grease. If no one else loves you, I love you. Later.